So the next speaker is Dan Sadot. I've ran into him, Dan, when was it? That was probably 100 years ago in the P-Cube days or one of those days. He's continuously been unemployed. Every company he was involved in got sold. But thanks God, he's not on the Social Security payroll at this point. And he's with, or was with the University of Beersheba at the time, where I do a lot of work these days with Jihad El-Sana, if you know him. And he will be the next speaker. So then the microphone is yours.
Thank you very much, Giora. And good afternoon, everyone, especially for staying here this long time. So myself, a few words about my background. So I'm still a university professor at Ben Gurion University. Also the founder and CEO of CyberReach, which is basically a startup company spun out of the university activity, doing kind of building a photonic ridge to protect cyber attacks. So this quick presentation I'm going to show, I'm just going to browse a new approach. It is not quantum per se, it is photonic for sure. And it is complementary both to PQC and to QKD. So going through a security challenge, probably it's a waste of time. All the people here know at least as good as I do know the challenge. But just to focus on what we're targeting. So high-speed optical communication is targeting the high end, like 100 gig and beyond. So I would say the major points of threat that are relevant for this kind of application that I'm going to describe is really the high end, data center interconnection, metro networks, long haul, submarine, and so on. And the concept is that even though there is a lot of work done on the key, on the way of encrypting the key, the data itself is always transmitted at very high quality, high SNR, and can be recorded. And now we only rely on how strong is the key for that. So that's kind of a complementary approach that we are proposing here. Of course, the threats, I'm skipping now to save time to all of us and all the publications about those threats. But just to think, the conventional approach is to apply the encryption on the digital level. Everybody knows that. The question is how strong is the encryption key. I think that a nice, I would say, analogy is like more than 100 years ago when Henry Ford was asking, what next do you want? People would say faster horses, the stronger whatever, but no one was asking for a car, right? So we're looking for a kind of a paradigm shift, and the paradigm shift that I'm going to show here is, again, a complementary photonic solution for QKD and PQC. So the idea is really to apply all the, I would say, manipulations on the photonic level. So you take the document, it could be encrypted perfectly, but digitally. Now we apply kind of an optical iron dome, so to speak, and we are transmitting the data into the fiber in an analog photonic way, which is non-conventional, non-natural, in a way that inside the fiber it is decomposed, turning to noise, to optical noise. And then, if it's being tapped, so the uneligible user is just receiving noise. The information is being lost at the instance of the recording and lost forever. So only if you have the key at the instant, like so to speak in the speed of light, in order to inverse the manipulation that are done photonically, only by that you can rebuild and recompose the information, else it is destroyed forever. And the connection to post-quantum readiness is that basically all the, I would say, manipulations that are being done offline after the recording, taking the digital information, trying to break the code and so on, all those offline manipulations are literally off the table because there is no raw material to try to break anything. So the only way to reconstruct the information is by applying the exact optical manipulation that has been done on the transmit side in real time, all optically, so to speak, in the speed of light. So, I mean, there are a lot of benefits. I'll skip that one. Just show you, like, briefly, that this, so to speak, magic does work. So we start with a conventional communication system, the high-end one, which is optical coherent transmission, like QPSK, QAM16, whatever. I'm not sure how much you're familiar with those formats. But the bottom line is that the system is very similar, and, in addition to specific modifications that are here circled in red. For example, the laser is not a regular laser, it's a mode-lock laser, which is short pulse laser, very broad in the spectrum. There is what is called here SPE, which is a spectral phase encoder, which is basically the optical key that is constantly changing every fraction of a second. And there is noise loading in order to bury literally the information below optical noise. So on the receive side, you must do basically the opposite in a way that you do have the equipment and the key, which is constantly changing. And we show that we can do it with a scheme that we call multi-homodyne coherent detection. I'm not going to educate you now on all the physics behind it, but just show you the intuition. So the intuition is that we start with the information that is being modulated with a multi-mode mode-lock laser, so many carriers. Those carriers are spanning over multi-terahertz, and the reason for doing that is that this multi-terahertz band cannot be recorded at once. There's no material in Earth that can respond in such a speed. The maximum would be like maybe 100, maybe 200 gigahertz, but certainly not terahertz speed. So that's step number one. Step number two, we decorrelate the different ingredients of the frequency by applying this phase mask, which is literally the key. And in that point, so all the information is now spread, cannot be recorded, and even not correlated. And just to put the last, I'll say, last nail in the coffin, we are attenuating it very aggressively, burying it below optical noise, and only at that point it is being transmitted to the fiber. So in the fiber, you just observe noise, optical noise. And now I hope I convince you that the information is ruined. Now I need to convince you that it can be also reconstructed by the eligible user. So I'm not going to, move it very quickly, but the idea is that we handle the receiver with a similar laser, which is a mode-lock laser. So we basically fold all the ingredients back to the baseband, basically turning the multi-terahertz information back to a multi-gigahertz, which can be recorded. Now, the way to fold it is critical. The big question is, what is the relationship between the key at the transmit side and the receive side? So if they are identical, it's one thing, meaning that the eligible user does have the key and it can make it identical. If it's not identical, it's a big problem. I'll show you just intuitively what's going on here. If the key is identical, so the phases are canceled and the summation of all the elements are being summed in a coherent manner. This is kind of a coherent addition in optics, well known also with the iron dome lasers that are now being spoken about. So it's a coherent addition that takes, for example, 100 lasers, turns it to a 10,000 times, like 100 square higher power. So we're doing similar effect for rebuilding the signal in a coherent manner, while the noise is, of course, incoherent, so it remains proportional to L versus L square. Bottom line is that the information is being rebuilt above the noise, all optically before the conversion to electronics again. So that's for the eligible. The ineligible user is just collecting the elements without the key. So they are being collected incoherently, similar to the noise. So if you start with negative OSNR, signal-to-noise ratio, you end up with the same negative signal-to-noise ratio, and you just record the noise. So that's the main intuition behind the technology, just to show you it does work. So this is a regular transmission. You see the spectrum of the laser. We're doing different transmission. First, we're spanning it very broadly. Then we're applying the phase manipulation, which is the optical key, which is being constantly changing, as mentioned, in fractions of seconds. And then we put the attenuation and noise loading. So the bottom line, this is what you see in the fiber. Left-hand side is a normal transmission. Right-hand side is the information which is being hidden here. Basically, it's in a stealth mode and cannot be recorded. If you record the noise, the information is lost. I can show that if you do the opposite, like removing the key and spanning back the coherence of the laser, so then on the right-hand side, you see the eligible user can reconstruct, in this case, QPSK signal. On the left-hand side, that's what the intruder or the unintelligible user will receive. You receive just noise, which is meaningless, and no quantum computer on Earth can help here. So that's the paradigm shift in the approach. Just to move on, there is a real product, because I'm also representing him here as a startup company. The product is already being deployed with some of the elite, I would say, agencies here in Israel. So it is already tested. It is not just science fiction. I can share with you that like a couple of years ago, I personally didn't believe it's going to work. It does work. It is fit into a product now, and it's being tested for more than a year by now. And just to finalize and to connect to the QKD approach, so here, if we do believe that the information is running in a stealth mode, protected and so on in negative OSNR, so why not transmit the key as well? So we are transmitting the key under the same photonic layer security level. So the left-hand side is for the data diagram, right-hand side is for the key. Of course, there is a lot of authentication mechanisms like Diffie-Hellman and so on, but the main differentiation is that everything is covered below this photonic layer security, so it must be manipulated in real time. So to speak, everybody is under the gun in trying to break any code. So even if there is a quantum computer that can't break the code, it doesn't have the time to do that. So bottom line is that I'm just finalizing now. We're transmitting every fraction of a second transmission that includes also the key for the next slot. The key is being extracted by the eligible user. He can translate it to the optical required manipulation, and so on and so on. But the uneligible user has no time to try to break the photonic and digital authentication codes. So the bottom line is that the modem is immediately down, no information, no raw material, and nothing to try to hack later on. So this is just a summary. I mean, three, I would say, recaps. This kind of scheme provides record proof, I would say, function, which I believe is not really existing for high-speed data, only for key rates. But here we're speaking about 100, 200, and 400 gigabit per second, which are fully secured. The technique is based on multi-homodine current detection, which is already tested, demonstrated, and even published, actually. And the photonic exchange is based on constantly changing the key in fractions of a second. And by the way, physically, from the physical point of view, the key can be changed every nanosecond, because there is technology to change phases in nanoseconds, in gigahertz. So you can assume that the key can be changed every nanosecond, and if you don't break the code within 1 nanosecond, it's too late to try to recover it. So I think with this, I will end it up. So thank you very much.
Actually, I misunderstood something. You see, the reason why QKD is, the quantum one is protected is because of no cloning. But any other classical thing is, as far as we know, is not protected, at least in principle. So why did you say that you know that quantum computer cannot decrypt
because the
this?
quantum computer needs to work on bits.
Yes.
If you cannot record I mean, this is an analog photonic scheme. If you cannot turn it into meaningful bits, so it doesn't really relate to how strong is the algorithm, because you don't have the raw material. You don't differentiate between, I mean, you record noise, and the noise, if you cannot convince yourself or us that the noise can be reconstructed to meaningful bits, so then the quantum computer is useless. So the real question is it really possible to record the information at this situation that I'm showing? And of course, there's a lot of cryptanalysis that we have done to show that if you don't have more than, I would say, a nanosecond of time, so you just record a signal which is with too low SNR, and due to information theory, it is too low SNR in order to reconstruct any meaningful data out of it.
Okay, I would have thought that this is just pseudo-random data, and pseudo-random data in principle can be decrypted.
But you cannot even call it data, because
Okay.
it's analog. So the word pseudo-random doesn't refer to analog noise, because the noise is created by an ASE, amplified spontaneous emission noise, which is physical spontaneous emission of photons. You cannot call this pseudo-random, right?
Okay, thank you.
One question is, how do you transmit the first key so the other side can decrypt it and then...
Yeah, that's a good question, and there is a detailed answer, which is too long. I'll just share with you the intuition. There are time slots, very short time slots. So let's assume even that the first time slot is public information that everybody knows. So the first key is known. But then, when you transmit the next key, it is being transmitted in an encrypted level, either AES, Diffie-Hellman, whatever, and a normal transmission, so you have the time to record it and try to break it. But with this case, only the eligible user can break it fast enough to use the next time slot, while the others will not do it in nanoseconds.
So they need kind of sync both sides.
No, not only sync, they need the time to break it. Oh, the synchronization is a conventional synchronization between time slots, which every modem knows to do that. Yeah, I assume you have the first key and you have the equipment. Yes. No, because I just answered that. I mean, you do have the first key and you do have the equipment, so you receive the first key, you can record the first slot, but then within the first slot you have an hidden information of the next key. In order to break the hidden information, you need to do two things: to break the AES, the Diffie-Hellman, and in zero time. So that's the differentiation between this scheme and any other conventional scheme is the time, not the algorithm. The time, you have zero time or nanosecond time to break codes. And there is no computer that can break codes in nanosecond. So actually, conventional computers will break it in 100 years. Maybe a quantum computer will break it in hours, but certainly not nanoseconds. Thank you.